Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I think we can get started now. Sorry for the interruption or the delay with yeah. So I'm Aaron Smith from Extreme Computing Group, and it's my pleasure today to host Paul Navratil from TAC, the Texas Advanced Computing Center. So Paul and I have known each other for over a decade. Yeah. So I remember when he was using small displays and single cores. So at TAC, he's managing the visualization software group, and he is visiting this week because of SC, so I talked him into coming over here and giving us a talk. So I think he's going to tell us some about their new display technology and the software they've been building.
Perfect.
Thanks for coming.
Thanks, Aaron. And thanks, y'all, for being here, and thanks to whoever's watching on the web. So my name is Paul Navratil. I'm part of the visualization group at TAC, which is the Texas Advanced Computing Center. It's part of the Vice Presidents of Research portfolio at the University of Texas. And we have a mission to service the advanced computing needs of the university, the Texas system, and through primarily NSF funding, the national cyber infrastructure. And so what I'm going to talk about today is some of the challenges we face as a visualization group at TAC and some of the ways we're solving those challenges both in our remote computing platforms and in our local large format displays. Okay? In terms of TAC or
number of people and
I don't have slides for that, but I can give you just off the top of my head. We're about 100 people, almost all at UT Austin at our research campus, about 10 miles north of main campus. We do have a few folks in remote offices at Office of Naval Research, down in the medical branch in Houston for UT. So we have just the beginnings of a branching outside. But otherwise, we're divided into visualization group, high performance computing, advanced systems that keep the big iron running, user support, and outreach. And so as part of our mission, our director, Jay Boisseau, it really has a emphasis on giving back to the community, not only the scientific community, but also the larger community, and both to inform the public and to inspire the next generation of scientists that will take our places. Okay, so basically what I want to talk about is how we're using the cluster technology that predominates high-performance computing today and applying that technology to visualization. Because as you'll see, once a simulation that runs on a very large cluster, 100,000 cores, for instance, the data produced by that cluster really can't go anywhere else. And so that cluster has to become the visualization and analysis instrument. And I'll talk a little more later about what that looks like in terms of what we do. So I'm also going to contrast the visualization workflow with traditional high-performance computing. If you think about, say, a fluid solver in massive parallel, you can just divide up the domain evenly, or say if you're doing a ionization study of dark matter, you can take each of your stars that emits the ionization and duplicate the entire universe that you're studying across different across your cluster. But for visualization, the computational workflow looks different, and the results and the demands placed on those computations are different as well. And we'll talk a little bit more about what that means. Then I'll also describe some of the solutions that we're pursuing at TAC. Of course, I'm being biased towards the one I'm more familiar with than not, so you'll see a lot of the software and some of the hardware that I've helped design. And I'll talk a little bit at the end about motivation for the work of future clusters. Okay, so let's look at what a typical HPC workflow looks like. Say you have some parameters that you input into an equation. So this could be, say, the initial conditions for a weather simulation, temperature, cloud density, and fluid in the atmosphere. You might have some initial conditions, some starting points, and you ship those into your supercomputer and run a simulation, and then you get some results, typically in the form of some graphs or maybe just even a single number or set of numbers. And you might also get some time steps out that you either feed back as new initial conditions or you do later analysis on. And so most of your work happens at the machine, and it's in terms of inter and intra-process communication. That might take the form of MPI, maybe p-threads, maybe some combination of both. Nowadays, you're also talking about hybrid technology, so GPU computing. Intel's making big announcements about Mike this week. There are many integrated core project that came out of the Larrabee development, if you're familiar with that work. So visualization workflow takes these time steps that were typically generated from some simulation. It could also be from an instrument, say an MRI scan, electron microscope, and runs visualization algorithms on some high performance or advanced computing hardware. And then you get some geometry, for instance, that you're actually going to render into a picture. You then have to feed that geometry back into some sort of hardware to perform rendering that creates the pixels of the images that you create. And then you have to display those pixels somewhere. And that can be an online process for interactive visualization. That could also be offline, say if you're rendering frames to create a movie. And typically, this process is iterative. So say you're trying to do a visualization and you don't like the technique you used. Maybe you did isosurfacing, you want to do volume rendering instead. So you change the way you're generating the geometry. Maybe you didn't like the color palette you used, so you have to create a different image. Maybe you have point data and you need to resample it into a grid so that you can use more visualization algorithms on it. So you have to actually manipulate the data itself. Then you typically also have a process where you're creating your rough visualizations just for your own edification. Then you polish it up a little bit and you show it to your colleagues. And then you polish it even more and you put it in your publications or in your talks. And so there's another axis of iteration that comes out of the screen. So what does this communication pattern look like? And I put this in quotes because I mean inter-process and intra-process communication similar to HPC, but I also mean the communication that a human gives to the simulation or to the process, and that comes back to the human, because there's typically an interactive component to this. So there's the same inter and intra-process communication. There's interactive algorithm manipulation. Think of changing the ISO value in an isosurface. And then there's also interactive display of the data. So all this process typically has to happen in, say, a 20th of a second for just interactive, or a 60th of a second if you want really high performance interaction. Okay, so the algorithms tend to be more demanding on the hardware than a typical HPC algorithm for a couple of reasons. First, the calculations tend to be more irregular. There's data-driven calculations. Think traversing a tree or searching for a particular ISO value in a data set. You also generate new data. So if you're doing that weather simulation, the region of the country you're simulating never changes, right? You may change the gridding of it, but once you've formed that grid, it's constant through the calculation. In visualization algorithms, you're returning new geometry, or you're generating images that you'll return. So you have to buffer that data in memory. Also, you're interacting with someone controlling the algorithm and controlling the calculation. And so if you're changing that ISO value, then your parameters change and you have to recalculate very quickly. And the users expect an interactive response. They can tolerate up to, say, 10 frames a second. But if you start getting into seconds per frame, where they have to go get coffee or check their email between them, you've lost it. And also interactive display of data. And particularly for large simulations, as the pixel count grows, it's more and more difficult to ship those pixels in a meaningful way to a display. Okay, so let me give you just a quick example if you're not familiar with visualization algorithms. Some work that we've done in GPU-based isosurfacing. So isosurface just means you're looking for a continuous value in the data set. Think the temperature lines on a weather map extrapolated to 3D. And a classic way to do this is with marching cubes, where you find where the value crosses in a cube, and then there's a lookup table to determine how the geometry is placed. And so, say if our value crossed the line 4.7, 4.5, and 4.0, then we go back to the lookup table and we put the triangle at the cross point through trilinear interpolation. Okay, and so the way this is done on the GPU is actually a three-step process. They classify the voxels, find out which voxels have your data value and which don't. You do a scan to determine where those voxels are, and then you compact them into an active voxel list and generate the triangles. Okay? The challenge here is that you don't know how many triangles you're going to generate ahead of time. And on a CPU-based algorithm, that's fine. You just create a new vector, or you create maybe an STL vector and just push onto the end of it. On the GPU, that's harder because until recently, you couldn't allocate new memory on the device side. And in OpenCL, that's still true. CUDA now gives you the ability to do that. So, but either way, you have to buffer some of your available memory for the data that's going to result. And so you can see that the execution time is really bad in this space because, one, of the multipass process, and two, because of the amount of global memory that you're accessing in that compaction step. And so one of the things we've done is whoops, that was back, sorry, is that we've now moved this. This is just summarizing the issues that I mentioned previously, that you don't know how many triangles you're creating initially, but also you're generating the triangles in parallel and you're writing them to a single buffer. And so the massive multiple threads in a GPU have to synchronize down into that single buffer. So think of it as a reduction, but with more data. So then what we've done is we just take a classic, you can think of it as an octree approach from graphics, that we just, instead of dealing with the individual cells, we create metacells that help filter out regions of space that don't, or regions of the data that don't have interesting numbers. And so we can now, in a spot that was 10 milliseconds, we can reduce that to 3 for about a 2 and a third times speed up. And we can also, because we're operating on fewer cells, the classification step becomes a little faster. But so I hope that motivates just a little bit, and if we can talk more about that work afterwards. I know I've given it just a very quick treatment, but basically the takeaways are that we need more memory than HPC algorithms, and that amount of memory we need is dynamic, or can be, and that the large problems need significant computational resources that may be larger than what is evenly divisible on a single node. For instance, we have done some work with the dark matter simulation where each individual time step is 650 gigabytes. And that is the memory footprint for the HPC simulation itself. For the additional structures that the visualization algorithm needs, that expands to 3 terabytes. And some of that is because the visualization space, VTK, is only now being concerned with memory efficiency. But some of that is just you need the extra space to allow the algorithm to work. And so if we need, what we find out is when we first started working on this system, our largest visualization resource had only a terabyte of memory. So we had to go back to the HPC resource, but we were allocating nodes now for memory instead of for processing power. And because libraries like VTK aren't multi-threaded, we would allocate the 32 gigabytes per node on Ranger, one of our machines, and 15 cores would sit idle. So there's definitely an opportunity, and this is some of what we're working on at TAC, is to parallelize this so that we can make use of those cores even when we're allocating for memory. Okay? Okay, so the original solution to all this was to move the data to a separate machine to do viz interactively. For instance, some data sets were small enough that you could move to your own desktop or to your laptop. However, as we're getting larger data sets, moving them off the machine they were generated is becoming untenable. So even if you have a 10 gigabit connection, a terabyte, go get a cup of coffee, a petabyte, go on a vacation, right? And if you have to do this over wireless, forget it. It's just not going to happen. We, even today, work on data sets where it's easier to put the data on physical drives and mail them rather than try to do the transfer. Okay? So, and this is only going to get worse because as the machines grow, the data sets grow, but the disk technology and the network infrastructure isn't there. And this suffers from a last mile problem. So at UT, we have 10 gigabit connecting our machine room to the main campus, but if I try to send that to UT El Paso, it's going to pass through a thin pipe, and that's only as fast as that transfer is going to go. Okay. So what we've done is we're moving the visualization resource to at least the same machine room, and ideally moving forward on the same machine. So our first system like this was built in 2008, Spur, which was an attachment to Ranger. 8 nodes, 32 GPUs, and a terabyte of aggregate RAM. And each single node had at least 128 gigabytes of RAM because there are still some legacy shared memory codes that need that much RAM. Longhorn is a machine we just put out in 2010. 256 nodes, 512 GPUs, and 13.5 terabytes of aggregate RAM. And because it's in the same machine room, we can put a very high bandwidth connection to the Ranger file system and operate on the data without moving it. And now our Lone Star system that we just released also in 2010 has right now 8 nodes, each with 2 GPUs, but we're going to expand that by the end of the year to 72 nodes with GPUs. So we have a smaller version of Longhorn sharing the same interconnect and disk as the larger nodes of Lone Star. Lone Star is a 20,000 core machine. And our new machine that was just announced, Stampede, which will be a 10 petaflop resource, released at the beginning of 2013, and yes, everything has a Texas tie-in to the naming scheme. So this will have 128 nodes, each with probably a Kepler GPU from NVIDIA, and also each node will have an Intel mic across the entire system, which will be on the order of thousands of nodes. So that'll be interesting to experiment with. And so for problems that don't operate on the Viz subsystem, we use software rendering and we move it back to the HPC cluster. Okay, so what about shared memory? There are some in the community that think shared memory is and always will be necessary for visualization. We've done the experiment ourselves. And Spur was actually a replacement for Maverick, which was a 512 core, 1K cores, half a terabyte of shared memory. And what we found is that we were able to build Spur with more capability for cheaper and easier to maintain. And the use of Spur was actually much higher than of the shared machine Maverick. And the nice thing is that if you go to a distributed memory model, you can get much more aggregate RAM than is possible on a single machine today. So you can get an order of magnitude more. And there are single nodes that you can get now that Lone Star and Stampede will both have that have a terabyte of RAM. So you can still get a significant shared memory resource even in a cluster environment. Yeah?
Can you give us sort of the one-liner of why shared memory failed for you? That is, this is great evidence that it did, but...
Sure. I think because the environment is harder to control because underneath you're either having a NUMA access that you don't have control over or you're slowing everything down to the least common denominator. And it's ultimately a shared resource. In our clusters, we can give everybody exclusive access to their set of nodes, whereas on the shared machine, everyone's playing in the same sandbox. And so, also, this is just following trends. Viz machines have always followed the path of HPC machines, and clusters have definitely won out. I think 480 some odd of the top 500 are cluster machines, and that's just going to grow. So we're trying to bring the community into that role. Okay, so there are some tools out there, some toolkits like ParaView and Visit. two large shared memory, large open source platforms based on VTK to do visualization. And what they've done is they use a fat client model where the geometry is generated on a server and then shipped to the client. And some of them, Visit in particular, tries to be smart about when it ships pixels versus geometry. But what we've done is, so we've seen that the data traffic, especially doing managed communication within the software, can be too high for low bandwidth conditions. And also, the connection options are still lagging a bit behind. Sometimes they just assume a large shared memory system that you're connecting to even remotely. What we've done instead is we push everything server side. And now we just use a thin VNC client to interact with the server. And that's been successfully used from TAC machines literally half a world away. We have collaborators in the Gulf states working on our visualization system remotely. And there's definitely latency in that model, but you're going to experience the latency either way, and this allows the computation to move forward while just moving keyboard and mouse movements from the user and pushing pixels back. And with the new VNCs, they're doing smart things like only updating the change region of the window rather than pushing an entire window across. And so this really minimizes the bandwidth. And if you want, we have full-featured GNOME or KDE on the back end, or I tend to use just TWM. Now that's ancient and Spartan, but it gets the job done, and it minimizes even the overhead of the windowing system. Okay, so let me show you just briefly. I won't play this entire video, but this is our web-based interface onto Longhorn. It's called EnVision, and so someone through the web can either get that VNC window I mentioned or go through an interview process to do their own visualization. And this is, I think this version is VTK based, but it has tie-ins where we can use other rendering solutions. And so you just have an idea that this all happens, again, in your browser. And this is a mummy MRI that they're playing with.
This architecture, how much is happening in the browser? How much of it is VTK window?
So this is all in the browser. So the VTK is rendering server side, and then the pixels are being shipped. Okay. Yep. So it's not even VTK window. Okay, so let's talk about image display, because generating the images is only part of the solution. Your analysis of those images are limited by the pixel count on your display you're using. And if you have an electron microscope that is producing an image that's 25,000 pixels by 25,000 pixels, you're either zooming and panning in something like a Bing Maps interface where you're zooming into what you want to see or pulling back, but you have to trade off context for detail. And so there are other images like NASA Blue Marble has a 3.4 gigapixel image of the entire Earth. Google Art Project has the large scans. Each museum in the project has donated a piece of art to be high resolution scanned. It's the equivalent data. This is at half-kilometer resolution per pixel, and it's equivalent to the entire Earth scanned at kilometer resolution per pixel is how much data are in one of these Google Art Project scans. So very high resolution, and again, the electron microscopy is at half a gigapixel already. And so it's nice to have both resolution and size, resolution to see the details, size to see the context. And so we have multiple display technologies in our visualization lab that give you an idea, that allow you to choose the technology that's right for you. And this is a brief view of the Viz Lab from the Longhorn network. This is all of the Longhorn network I've seen. I don't know if you're following that saga, but apparently there's a neighborhood in Dallas that has the Longhorn network, and Austin doesn't. So that was our 307 megapixel display. That's a 12 megapixel touch display. And we actually have that touch display in our booth at SC. So if you have an opportunity to go to the exhibitors fair, it's at booth 323. And so this is just a minute. You can see high resolution photography. The lab has allowed us to expand beyond the traditional STEM fields: science, technology, engineering, mathematics. We've gotten fine arts, architecture, humanities in here to take a look at. We've actually had artists build pieces for the Viz Lab. And so what we found is by working with the artists, they have the vision of how it's supposed to look, and they challenge our technology to reach it. Then we can take that new ability and bring it back to the science and engineers to expand what they can do. And so we find it's a virtuous cycle to work with these folks. This is a 3D display. This is just an 82-inch commodity television and driven by a Quadro graphics card. And so what we've done, this replaced a Barco projector solution, 2,900 square feet. And in the space that projector, that single display of projector technology took up, we have a meeting room and 6 high-tech displays now. So we still have a projector, but we also have so much more that we built and we maintain. And the power of the commoditization of this hardware has really come to the fore. Okay, so this was our first tile display, Colt. 3x3, these are 30-inch LCD monitors, and we built the frame ourselves. Just any drafting program that gives you actual measurements, you can design it, send it to a company. It's called 8020, the industrial erector set, and they'll cut it, send it back to you, iodize it any color you want. So as long as it's black. So this is the 307 megapixel display, and that's showing Mars in the background, plus some visualizations on top of it. And the nice thing about this is you can either show very large data, or you can show multiple views of data or correlated data. And so you can have everything up at once rather than having to switch between windows on a smaller display. Our work here has also been starting to expand beyond just our center. We run a lab in the College of Education at UT now that allows them to work on their information visualization problems that we have a partnership with, such as the scores for every student in California in 1995, the test scores for them. And so those are the types of problems that they're trying to visualize. We've also consulted on tile displays at UT San Antonio, UT El Paso, and I believe also in Colorado. And so that's broadening out. And again, built and maintained all by tech staff and using commodity equipment, so also at a fraction of the cost. This is a schematic of Stallion. You don't have to read it. The takeaway is it's 75 displays, 30-inch. There's a 3x5 hotspot just by a feature of how the hardware worked out. The outside that hotspot, each GPU drives 2 displays. Inside the hotspot, each GPU drives 1. And so you can have there's a notable rendering performance boost in that hotspot. 23 workstations, and these at the time, this was built in mid-2008, there were no server class machines that contained GPUs. It was really at the birth of the GPU revolution, so we just got gaming boxes. And these are G80 GeForce machines driving it. If we did this today, we would use server rack-mounted machines that contain GPUs, and we'd use Quadros. And we have SDR InfiniBand just to have high bandwidth among them. And that's it. We also have a 5 terabyte file system that's in the process of being expanded to about 50 terabytes. Okay, displaying data. So that square is a scale representation of the 30-inch monitor compared to Stallion. Okay? And then that Blue Marble project I mentioned, so this is to scale 3.4 gigapixels versus 300 megapixels versus 4 megapixels on the single display. So you can't see the entire image, but which one would you rather look at that image on if you had the choice of either in your office? And so the point being, you can't see all the data, but you can see more of the data at resolution so that you can see not only the details, but get the context. You can almost see the Great Wall on that. It's pretty cool. Okay, so display software is not standardized at this scale. The Cal IT Squared team has built CGLX. Those were really the first folks, and then folks at Chicago have built Sage, but they're now both closed source. And that's a problem because some of the configuration assumptions are baked in. When we first got Sage, we had to modify it. It was open source then. And we have to run CGLX in a degraded mode because it doesn't accept our hardware configuration naturally. And full-featured windowing environments like XDMX don't scale. There's actually hard-coded limits in the code at 16 displays. And so 75, we just uncommented it and see what would happen. Bad things. So there's definitely a need for folks to do X right. And because outside of a full-featured environment, your ability to have software hosted on the large display is limited as well. Primarily images and video streams, because that's the first thing people try, and it's relatively easy. You have an API for third-party software, but if you want to run a closed-source proprietary piece of software or a large software base, you would have to go in and modify it. You can use something like Chromium to just sniff the OpenGL and map it across, but that Chromium stopped development in the mid to late 90s, so it only supports OpenGL 1.3. And we're at OpenGL 4 or 5 now, so a lot of stuff that it doesn't support. And then to give you that pan and zoom feature for very large images, there's a separate application in Sage, and CGLX doesn't have support for that at all. So what we've done instead is we have now beta released our own DisplayCluster software that will remain open source. And it combines the features of Sage, CGLX, and Magic Carpet is that pan and zoom for large data or for large image. And it has all of those features, plus it allows you to toggle between choosing network bandwidth versus disk bandwidth. For if you say we had a development event before a UT football game, and we streamed 75 historic football games on the tile display, which was really cool. And it was kind of amazing they gave us the copyright permission to do that, but it really taxed the ability of the other software programs to do that, and so we had to run it in our own software. We are also exploring a touchless interface, and you'll see a video of that in a moment. And we also have TUIO Bluetooth connectivity, so you can use smartphones and tablets to control the display. And we also are giving a Python scripting interface so that you can demonstrations or do advanced scripting for interactions across the display. This was really motivated initially by our artists who wanted particular images to come on the display at a particular size at a particular point, and the other windowing environments really couldn't handle that. Okay, so let me show you a little clip of this. And so this is showing that pan and zoom that you would normally have to have a separate application open for, and now in DisplayCluster we can show multiple images and zoom into them simultaneously. These are some of those Google Art Project videos. That's Van Gogh's Starry Night. This is the ambassadors from, I think, the 17th century. And the nice thing about it is everything's public domain, so we can put this up. Here's the Connect interface. We liked that. That's right, that's right. So this is a piece of 17th century Russian art, and we were amazed that that face looks a lot like Robert Downey Jr., particularly after a bender. It's a little green tinted. And so, again, part of the motivation for this is the College of Education wanted to use Macs to run their cluster because they have a relationship with that. And so CGLX and Sage wouldn't run on the Mac. And so that really motivated us. We'd talked about it a long time, but once we had a tangible problem to really address and fix, that's what motivated us to do it. And we've already had a lot of interest from all of the UT institutions that have tile displays. Folks at Stanford are interested, University of Central Florida, University of Michigan. So I think that folks are using what's out there now because that's what's out there. And so hopefully we'll have some nice moving forward experiences about how our stuff works. So this is the touchscreen display. This is I think that's Bing Maps being over the University of Texas. This was designed in-house from 6 46-inch Samsung LCDs, a PQ Lab 32-point IR frame. We also have a pane of glass in front to give a smooth swipe experience over the bezels. And then we also have the Kinect to do a touchless interface. And this is really working as a test bed to then take those interface designs to the larger displays. And so there's a nice feed back up. And it's driven from a single node with an AMD Eyefinity 6-port GPU. That really allowed us to keep the costs down. I'll talk a little bit more about this later. The challenge there is that it has really reduced rendering capacity because it only has 4 gigabytes. It's driving 6 displays at 2 megabytes each. And if you're trying to stream, say, a video on each of those displays, things break down pretty quickly. But it's also doable into Windows 7 and Ubuntu. OK, I think this is the last video, but this gives you a little sense of how the display works. So this has been motivated by a project with the National Archives. This is showing the digital holdings in a tree map view. And the National Archives are really struggling because they just don't understand half of what they have in digital form, much less how to respond to a Freedom of Information Act request. And so this is operating to allow those folks from the School of Information and from the National Archives to really interact with it in a more dynamic way. So let me get to some of the interaction. That's just one of the demos. There's multi-touch map navigation. You can see the whole video on YouTube. So that's Bing there. I'll tell you, that's one thing. You have to actually hold that and then do the rotation. Google Maps lets you do a gesture like this to do that rotation. So any Bing developers in the audience, that'd be a nice feature to add. OK. So let me talk a little bit now in the last few minutes about what the types of things that we're doing on these displays and some of the user successes that we've had. So this is really something that could only happen at Texas, I think, is after the BP oil spill, we had scientists who have models of how the Gulf Coast, how the Gulf, the patterns of ocean currents in the Gulf, and they then just modified that code to track where the oil spills are going, where the oil particles are going. So I lied, that wasn't the last video. Whoops, did I pause it? So here's a visualization of that simulation, and these were done, the simulations were done in real time so that we could give the responders some idea of where the oil might be going. And so you can see how this is the end of Louisiana, this is the Mississippi, and coming into the New Orleans area. And so the simulation was also run at multiple resolutions so you could get the coastal effects and then also track more broadly in the Gulf. So this, on this video itself, or just in general, yeah, so you can zoom into to really fine-grained. Now the simulation has granularity limits because it's a Gulf simulation, and so at the coastal elements are rather coarse, but the simulation itself was pretty accurate in terms of where the oil was going. And so this is in the spirit of what we do with NOAA during hurricane season. We have several 100,000 hours of compute time set aside so that when the plane flies through a hurricane, they can take those immediate readings and then they run what's called an ensemble simulation, where they run really about a dozen different hurricane simulations with slight parameter tweaks or slightly different implementations simultaneously, and that's where they get that cone of probability from. They just average the simulation results together. Back in when Ike came through in 2008, our supercomputer actually predicted that at the moment that the storm was going to go over Austin and cause the UT football game to be moved a month later. And then the storm took a right turn and missed us entirely. But it was, it was our claim to fame that we got the game canceled. So we've also studied H1N1, not only the molecule itself and how the virus attacks cells, but we've also looked at the epidemiologic effects. And this is a nice web interface that Greg Johnson on my staff has developed. That part really isn't exciting. So here, I think we're getting a little choppy, but you can see the counties of Texas, and then once you zoom into a particular point, you can look at the results of the simulation. I wonder if I broke things. Yep. So you can see the counties are changing color by how much infection is occurring at a particular time. And you can see how it radiates out across the state from a particular input. So that was a disease that was breaking out in Travis County, where Austin is, and then how it slowly follows the population around in the state. And this is something that was commissioned by the Texas Department of Health so that they actually want to use this to track Texas epidemics and to prepare for future ones. And what you saw there was then the graphic output of amounts of antivirals, amounts of folks who are susceptible to the disease and who have recovered, or the mortality rates. And so this is a really powerful way for those folks to really learn more about what's going on in terms of Texas health. Okay, we've also worked on high-resolution mantle convection, and what that allowed us to do, this work was featured on the cover of Science not too long ago. That allowed us to then, with the same team, do a simulation of the Tohoku earthquake. Whoops. And so what you'll see here, this is work that Greg Abram did, is the seismic wave propagation that originates in Japan in the top corner here. So there's Japan. I assume this is right. Looks like the screen froze. I think the system's having a little problem with it. The video should be smoother, but what you'll see is that here, as the earthquake waves radiate out, watch in that center here, the waves actually hit the core of the Earth and reflect back up. And you can see that in the simulation eventually. And so here it comes. There's the shadow of it right there. And so that's part of the reverberative effects of the original quake. It really rings the earth like a bell. And you can see that waves propagating all the way out. This is through Alaska, down the western coast of the US, through Greenland and into Russia. Okay. And so this is another piece of visualization from that NARA project with the National Archives. And so this is 3D visualization or 3D imagery that the National Park Service has, plus photographic tours. And so this allows them to see where those particular files are located. So to summarize, let's talk about the trends that visualization systems track HPC systems, both at the large scale and at the small scale. The reason that we could build a system like Stallion or like the touch display is because of the power of individual workstations nowadays. And that viz systems must be able to scale to HPC size, either in the raw hardware or in the software that has to run on the visualization systems. So, for instance, a multi-threaded Mesa or other software rendering package would be excellent to develop. And advances in the GPUs themselves, not only in the compute where we can move the visualization algorithms onto the GPU, but just in terms of their display power, allows us to really increase the density. Although as we increase the density, it limits the power of the display. And so in terms of expanding a single window for like Bing Maps or for Google Maps, that's fine, but to do high-intensity video streaming that's either CPU or GPU intensive, a single node does show its limitations. But that power allows you to trade off. And so you can design your system either with many nodes to make it a proper compute resource in addition to display, or you can minimize the nodes to reduce the cost and still have a very large format display. For instance, if we were to redo Stallion today, we could span anywhere from 7 to 38 nodes, depending on the amount of compute power we wanted behind the display. And so for future work, we really, as a community, need to address the algorithmic inefficiencies in terms of the visualization stack. Memory efficiency, VTK still has an annoying habit of moving the data set into an unstructured grid, even when it doesn't have to, especially when there's a structured grid algorithm that can be more efficient. The raw VTK library still may do the dumb thing. Both the Visit and PairView teams have re-implemented a fair amount of the VTK stack to avoid situations like that and to use the fast case when possible. We're just starting to explore as a visualization community how to include accelerator support. We're already using the GPU for rendering. If we can move more of the algorithm down there and generate the geometry that we're going to render already, then more to the good. And again, improved software rendering, particularly for HPC systems that don't have graphics support. Right now, we really only can use the Mesa library, and that's single-threaded. And in terms of the usability for large-scale displays, the windowing interfaces are still limited, though we at TAC are working to fix that. Distributed rendering support, Chromium is the latest effort that I'm aware of, and that was at the end of the mid-90s. So that's 20 years old, or almost. And then better usable user interaction, and that's what we're working with both in touch and touchless interfaces, or using the interfaces that people carry around in their pockets, our smartphones, to actually allow us to use the displays. And with that, I'll open it up to questions. Thanks for your attention.
So I have questions.
Yeah, go for it.
So I was interested in the utilization of Connect. So what exactly can you do with that interface? Because on the video, right, the guy's kind of struggling to touch something down here.
So that's with the touch. With the Connect, that allows us, especially on a display like Stallion, to have a centered control point and then expand more of the display. We're also investigating using multiple Connects to do three-dimensional sensing, not just in front, but also getting a side sense, and then doing a chain of Connects to have control through the expanse of Stallion instead of just one in the center, so you could be at the side of the display and still have effective control. Part of the challenge is determining clicks. So if you want to grab a window and move it, you have to have some sort of gesture, maybe closing a hand so the surface area is reduced. I think the gesture we're using right now is kind of a Pac-Man, I want to grab this and move it. So that's part of a challenge too. There's work out there on using gloves or some sort of color coding system and cameras. We're trying to simplify the equipment needed. We don't want to have Michael Jackson gloves for everybody. So, yeah.
So this guy sitting behind me, look at your picture and whisper, bezels, he's got bezels.
He does.
So, how much pain do you find users experience from, having bezels across,
If they notice it at all, they notice it the first time, and they grow increasingly resilient to them. We're used to looking out of things like windows, and if you're looking out of a window and you want to see something behind it, you move your head. Here you just move the data. What it doesn't do well is PowerPoint. If that text is behind the bezel, you're not going to read it. And so we have a 4K projection system that gives us that slideshow. I did my dissertation defense in there on the 4 megapixel screen. We had another dissertation defense with the 4 megapixel slides and then the data all across Stallion in terms of videos, stills, and it was 10 but 10 video posters of his work, and it was very compelling. The bezels give us also some other advantages. Initial purchase cost, because these are commodity, we don't have to do any modification, we just stick them up there. A replacement cost, we actually have, you may have noticed in the video, some of those workstations. Those are the same monitors as in Stallion, and so we have hot spares that we can essentially just pop in there. The only caveat on that is you want the same manufacturer lot, because the fluorescence has slightly different temperatures, and that gets messy. Let me see. And then the construction and maintenance ourselves also, if you ever come to Austin and are right up with Stallion, it's not a precision fit. And so those bezels buffer us a little bit, and so we can just put them together, without shimming it or doing any sort of touch to it. Whereas the Barco system that we replaced, we had to pay a 5-figure contact for someone to drive up from Houston every 6 months and readjust and realign to account for building shift, thermal expansion, things like that. Another thing is those Barco systems had to be kept at about 60 degrees, and so the students would come in their winter jackets, wouldn't want to stay there. The entire walls were painted black to have this immersive experience. Here, we've made it warmer, people want to be in there, and because it's all commodity parts, it's used to being in the same environment as humans. It's made to be in an office, so we can keep the room at a balmy 68 or 70, and people can stay in there.
And the 75 monitors heated up to 84.
Exactly. There is a thermocline as you move forward. We adjusted the HVAC so that it now has a row of registers that blow straight down on the display. But it's 2,900 square feet. It's pretty reasonable. It doesn't get too hot in there.
We did a 18-panel wall, and we found that the amount of power we were sucking down was substantial. I was wondering about your power consumption with 100.
So I know the stats in terms of amps, just because when we were doing the circuitry on the wall, we wanted to make sure we weren't going to blow anything. The display is determined by the brightness of the monitors. We have it probably at about 1.5, which is just the default turn on. If you max the brightness, it goes to about 1.8 amps. If you minimize it, you can go down to about 0.8 amps. We, as part of the renovation, put glass doors in so that people could see the display as they go by in the hall. So we tend to keep the display on with interesting things, and it's great. You literally get these, pauses and walkbacks for people wondering what's going on in there. The machines themselves are rated at 8.3 amps. Warm boot is about, if I remember correctly, maybe 1.2 amps, and even running, it wasn't LinPack, but it was another stress test on it, never got above 2.5 amps. So that 8.3, I'm not sure where they get that, but that is extreme, crazy, doing something. So our normal operation is, I'd say, for the entire system, we're probably under 100 amps, which is still a lot, but I think for the size of the display, it's pretty reasonable, and compared to a data center, it's not moving the needle. Good question, though.
So right now you have people coming in and using it.
Yes.
How is there? I can imagine to a certain extent that they can't do their typical things on here. So they've got special apps and that's where they sign up. And so is it mostly sort of a showpiece right now, or do they actually get some work done?
There's a lot of outreach that happens here, and education coming through. For instance, the electron microscopy. the lab came in, they loved it. The PI was, a 40-ish, woman, and she'd never touched a game controller, and it took 15 minutes to pry it out of her hands because she was zooming around and, exploring it. Great, Their 3D reconstruction technology, the science they're actually doing is like a keyframer. They stack these slices together and then recreate the neurons in 3D. Software is single-threaded, runs on a single workstation, doesn't utilize the 23 nodes of Stallion. And so while we could bring up those images at the flick of a button, which they loved, their actual software didn't run there. And so what we do as a center is we do have funding to do advanced user support projects of porting that over. But there's also the last mile problem of this isn't in my office, this isn't in my building, I can't walk outside in the Texas summer, So there has to be some motivating factors for that. But we do have folks using, we're actually expecting to get more out of the fine art side, because to be able to zoom in where a brush stroke fills an entire screen, especially of something like the Birth of Venus that's in Italy, and it's a fresco, so it doesn't travel, that allows folks, it doesn't replace interacting with the piece, but you can get a much different experience with it. And then the science follows. In terms of an analysis, rather than big data, I think we have the multiple views gets more use. Where, for instance, for hurricanes, you can put path of the storm, you can put the ensemble forecasting, you can put the storm surge, all very large and together. And so they can analyze it as a group, and then they bring in the news media, and it looks great there too. If you go to the Texas website, just the homepage, the new campaign video for development was shot in the lab. And so we have the university president, we have all the students, and probably about 60% of that footage was in the lab. And even though we're a 10-year-old center, we have top-ranked machines in the world, there's still folks on campus who don't know we exist. And so in terms of a ambassador and outreach piece, it's already worth what it can do, and the science we can get out of it is in some ways a bonus. Yeah.
The Cal IT, any of that super high-res video conferencing stuff that they've been doing?
Yeah, and so we can do that as well. That's one of the things we wanted to design into our software. We had one of the lead developers for Sage was on our staff for a time. He's since gone to Schlumberger, but at Supercomputing in Portland, we had a live video stream to our small display Colt from Australia. But that comes back to the bandwidth problem. We had to set that up with National Lambda Rail to get a dedicated 10 gig connection, a whole lot of hoops to jump through, rather than to just use Skype and call Aaron on a Sunday, right? So, yeah, exactly. So, in terms of high stream data, the interesting takeaway from that experiment is that the compressed video actually looked much better than the raw. We did compressed and raw HD stream, and just the amount of packet loss in between made the raw stream really noticeably janky, whereas the compression actually, that's a technical term, but the compression actually recovered from that a bit.
All right, no more questions. Let's thank our speaker one more time.
Great, thank you very much. I appreciate it.